Okay, good morning. We're going to make starts. Okay, so we have done 4 lessons of revision on electricity so far. We're only going to do 6. So there's 2 left, 1 today, 1 next lesson, and then that will be us done. Because I teach you 4 lessons a fortnight, that'll mean that we have a handful of spare lessons, maybe 2 or 3 at the end. So I think they fall after Easter. We'll be able to use those for kind of generic revision across the sciences. So you'll be able to bring stuff in with you and you revise biology, chemistry, or physics, whichever one you feel that you need to do more of. But 2 lessons left on the physics. One of them is on electrical power, and the other one is on mains electricity. And I've kind of got a little bit out of sync with the 2 classes that I teach. So I happened to do the mains electricity one yesterday afternoon, and it's still on the board when I came in this morning. So I thought we'll just swap them around so that I don't have to write it up a second time. It doesn't really matter what order we're doing it in. So on Google Classroom, this is actually listed as lesson 6, but we'll go back and do lesson 5 next time. Like I say, it doesn't matter what order we're doing it in. So I'm going to quickly revise mains electricity now, take me 5 or 6 minutes, something like that. And then there are a set of PDF questions from past papers that you can get on with if you're feeling confident. And if you're not feeling confident, you'll be able to get one of the textbooks, either the blue one that you've been using all the way through or one of the revision textbooks, and you can do questions from those which are a little bit more scaffolded. That means they kind of hold your hand and build you up gently rather than throwing you straight into the exam questions. So it'll be your choice what to do when I finish talking. So you can write this down or not write it down, but I'm not going to rub it off. So if you are going to write it down, don't do it now. You can do that in a minute. Let me just go through it with you. Hopefully this will be familiar because this is one of the first revision lessons that I asked you to do in the last week of the lockdown work. I gave you some videos to watch and some questions to work through. So hopefully you've already revised this about a fortnight ago, but here we go. So mains electricity splits into 3 bits. We've got safety, basically making sure that it doesn't kill us because it is lethal and we need to be careful with it. Then there's kind of what is it? And then there's how do we get it to our homes? So this is the biggest section. So let me start with this. You need to know about plugs. You need to know what they're made of. Like plastic is a good insulator. The plastic that we wrap around the cable, it's a good insulator. This means that we don't electrocute ourselves. The individual wires inside the cable are wrapped in plastic as well, again, to keep them insulated from each other this time. And also we color code these so that we make sure that this end is connected in the way that the other end of it expects it to. If it's a TV, the other end of these 3 wires is going to be connected to bits and bobs inside the TV, and it's expecting this end of the wire to be connected to these pins. So you need to know which way around the colors are. So the one with the fuse, that's the live wire, and that gets a brown color. The one on the opposite side is the neutral, and that gets a blue wire. And those are the 2 wires that you would ordinarily, plug into a power pack, the kind of electricity in and out wires. They build up the main circuit. And then we've got this stripy one, which is actually yellow and green stripy, but I haven't got a yellow pen. And that's the earth wire, and that's a safety feature. Which brings us on to this bit. So the fuse and the earth are the main bit that you need to get your head around. The fuse is a thin piece of wire that melts. Could you not use any word except melt, please? It doesn't break, it doesn't explode, it doesn't dissolve or anything like that, just melt. That's all you need to use. And why does it melt? It melts if the current gets too high, in particular if it gets higher than the rating of the fuse. So all fuses have got a number printed on them, 5 amps, 10 amps, 13 amps, and if the current hits that or goes any higher than that, it'll melt. So if you've got a 13 amp fuse and 13 amps of current starts flowing through the circuit, then the fuse will melt. It's a safety feature to make sure the current never goes too high. So why might the current go too high? Well, in a bad example, the current might go too high because you've just put a knife inside a toaster and there's a load of current flowing through you, electrocuting you. That would be bad. However, that's not what the fuse is primarily for, because it does take half a second or so for the fuse to melt, and you can quite easily get a lethal electric shock during that half second. So it's not there for you causing the fuse to melt. It's there because the earth wire melted it. So what's going on there? So the earth wire is connected to the device in such a way that if a fault develops inside the device, a huge amount of current will be allowed to flow down the earth wire. And that huge amount of current is the extreme current that will melt the fuse. So the earth wire causes the fuse to melt by allowing a large current to flow in the event of a fault. This means that the fault is neutralized because the fuse will melt and no current can flow in the circuit. And that means that whatever the fault was, it now cannot pose a danger. It can't cause a house fire. It can't cause an electrocution in the future. So it's kind of preventing future problems because it's recognized that there's a fault now. So fuse melts because the earth wire allows a large current to flow. When we did this first time around, we spent quite a lot of time on this, but when questions come up on exam papers, they're only like 2 marks long. So you don't have to get into a huge amount of detail here. What I've just said is sufficient. Any questions about safety of mains electricity? Okay, let's talk about what mains electricity is. So again, this graph should be familiar to you. It's the kind of graph that you would get if you charted the potential difference over time. So for a battery, it would just be a nice straight line because batteries have a nice constant potential difference of, say, 1.5 volts. But this one, the mains electricity, it goes up and down and up and down. It's not constant, basically. It goes positive, negative, which means that the electrons in the wire, they flow one way, then they stop and flow back again. Then they stop and flow the other way, and then stop and then flow back again and stop. So we use this phrase, alternating current. And if you're ever asked what AC means, yes, it means alternating current, but what does alternating current mean? It means it keeps changing direction. Please use the word direction. You can also say it keeps changing size, but a better answer that's less ambiguous is reverses direction. The 50 bit means that it does it 50 times a second. So it goes forwards, backwards, 50 times a second. So every 50th of a second, it completes one cycle of forwards, backwards. You will not have to do any calculations with this number ever. So if you find yourself putting 50 into your calculator in a mains electricity question, you've done it wrong. We don't calculate with this. We just ask you what it means if we do. The 230 is kind of the average voltage because sometimes it's very low, sometimes it's very high. It averages out to 230, somewhere in the middle. Why do we want you to know that? Because there are loads of formulae. If you just glance at the yellowy poster at the back of the room, those 5 formulae all about electricity, the charge transferred and the energy transferred, 4 out of 5 of them have potential difference in it. And if you are talking about a device that is plugged into the mains, we expect you to know that in all of those formulae, the potential difference is 230 if it's something that's plugged into the mains. And the reason that we need safety features like this is because of the 230. A battery is 1.5 volts, and that's just not enough to push a current through the human body. It's not enough to electrocute you. 230 volts is enough to push a current through the human body. It is enough to electrocute you. So this 230 volts is also the reason why all these safety features are necessary. Any questions about what it is? Very good. Last one, how do we get to your house? So we spent a long time on this, and we met that there were pylons, which are the big metal things holding up the overhead power cables that come from a power station to your homes. So that's, I guess, just general knowledge. But the bit we focused on was that there were boxes at each end called transformers, which alter the electricity for transport. So it comes out the power station, and then this is called a step-up transformer that takes it up to a very, very, very high voltage, maybe about 400,000 volts. And then a step-down transformer that brings it back down to 230 volts at your house. So these 2 boxes are just for the overhead power lines to have very high voltage in the power lines. We did spend some time on transformers looking at how they worked, and there was a formula to go with it. But as I've written on the classroom post, how the transformer works and the maths of it is not going to be assessed. So you don't have to worry about that. All you need to know is that the transformer makes the voltage very, very high at the start, and then it brings it back down to very, very low again at your house. But you do need to know why we bother. And I want you to remember that if it is high voltage, then it will be low current. And we like low current because when current flows through things, it heats them up. And we don't want our power lines to be getting hot, because if they get hot, they'll be radiating heat out into the environment, and that's wasting energy. We'll just be heating up the countryside instead of sending the energy and the electricity to our homes to power our devices. So we don't want to waste energy in the power lines. So the way to do that is not to put very much current through them. So if you have high voltage, you can have low current. And if you have low current, you will not waste energy in the power lines. Top misconception about this is that people say, well, why don't we just insulate the power lines? We'll just wrap them in cotton wool or something, and that'll stop the heat getting out. But you're missing the point if you think that. The heat is already in the cable as heat energy. The cable itself is already hot. Whether it leaves the cable or not, you've already wasted your energy as heat, heating up the cable, even if you didn't heat up the environment. So we just don't want the heat at all. So wrapping this in insulation isn't going to help. We need to not have the heat in the first place, which means keeping the current low. Any questions about that? Very good. Right, if you want to, you don't have to, you've got it in your book already, but if you want to, there are some revision notes. Otherwise, like I said at the beginning, you have got various sets of questions available to you. There is the blue textbook that you've been using all year. There's the revision textbook on the shelf over there. There's more revision stuff on Classroom. A couple of weeks ago, I posted an electricity revision all about mains, and that's got chapters from the textbook in it. But the post from the current section, the revision section, it's under lesson 6, mains electricity, and there's a PDF there of past paper questions. And if you feel ready, that's the very best revision you can do. The lesson 6 PowerPoint PDF on past paper questions. Okay, this lesson is solo, so you can help each other out. You can talk to each other, but try to avoid chatting.